Hey guys, so we're on question 5 here. This is the one that was due, I think Tuesday, I'm not sure. The minute I see this, I'm thinking circular motion problem, which it is. All right, so a spacecraft of mass m in a clockwise circular orbit of radius r. I'm just going to circle my allowable terms here when I start doing this stuff. Around the Earth, as shown in the figure above, has Earth's mass right there. In the figure below, draw the forces, not components, that act on a spacecraft. Each force must be represented by a distinct arrow pointing away from the spacecraft. So it's going to be the pull of gravity right there. And it says draw and label. You don't label it, you lose a point. Going right to scoring guide, you get 1 point for an arrow towards the center of the Earth. You get another point for labeling it, and then it says note a maximum of 1 point may be earned if extraneous forces are present. If you put anything else on there but that, you lose a point. And you know that because I've told you that in the past. All right, derive an equation for the orbital period t of the spacecraft in the allowable terms. Any physical constants, that's like big G for the gravitational constant, as appropriate if you need to draw anything other than that. All right, they don't want you to add anything to that drawing up there. So let me get a piece of paper. We've actually done this in class. We've done this on the putting Hollywood to the test video. Not video. Thing that we did. I think it was with the Red Planet video, with the girl walking around that circle that was around the spacecraft. But anyway, so we've got the force of gravity on it. Can't use mg because we're not on the surface of the Earth. We've got to use the force pulling on it is big G, m1, m2 over r squared. Now let's make this formula particular to what we were given. We've got Fg equals gravitational constant, the mass of Earth, the little mass, I'll make this big masses, that'll show a big mass, little mass, which is the mass of the spacecraft, divided by, I think it was a capital R, right? Yes, capital R. Right? Then we're going to say to ourselves, well, that's now a centripetal force. So I'm going to set this G, the mass of Earth, mass of a satellite, divided by R. Oh, I almost did the biggest mistake in high school physics, got my squares. Set that equal to a centripetal force, which is mv squared over r. Okay, we've got m's on the left and m's on the right. Which m cancels out? Well, in circular motion, that's always the mass of the thing in the circular path. The thing in the circular path is the spacecraft. So let's cancel that out. Now I've got v squared over r equals G, mass of Earth, over r squared. That r and that r are the same, so that cancels with one of those. And now we're at v squared over nothing, should have written that, equals G, mass of Earth, over r. Now you're saying, how does that in any way get me to derive an equation for the period? Now the period is a very particular time. It's the time to complete one full cycle, or one full circle in this case. So since this is uniform circular motion, that's a constant velocity. I can replace that with distance over time. Now that whole thing is squared, equals G, the mass of Earth, over r. The distance to go around once is 2 pi r, because it's a circle. Time to go around once is the thing we're looking for, period. So the total distance you went around divided by the total time it took to go around is your velocity. the whole thing gets squared. I'm going to run out of paper. Okay. I'm going to square the left-hand side. 2 squared is 4. Pi squared is pi squared. R squared is R squared. Divided by T squared. That all equals G, mass of Earth, over R. I gotta get a piece of paper. All right. Right now, the challenge is to solve for that. So let's do this. I guess you could cross multiply if you wanted to, or just flip everything, right? T squared over 4 pi squared R squared then would have to equal R over G, mass of Earth. So I've got to take all this, put it up there. T squared then would equal, well, R squared times R is R cubed. So we get 4 pi squared R cubed all over, whoops, G times the mass of Earth, excuse me. Squared both sides, and there's your answer. Let's take a look at the scoring guideline. Well, I think we covered everything there. Oh, they'd even let you leave it like that. It's a little surprising. And the last thing, wait a minute. Nope, it's not the last thing. Second spacecraft of mass 2M is placed in a circular orbit with the same radius r as the orbital period. Or is the orbital period of the second spacecraft greater, less than, or equal to the orbital period of the first? That doesn't change. It doesn't change because the mass of the spacecraft canceled out. It's not in your solution. So it has nothing to do with the problem, which happens a lot in circular motion problems. And that's how you explain it, by the way. Go back to the formula you just derived and say, according to that formula, the mass of the spacecraft has nothing to do with the orbital period. All right, last part. The first spacecraft is moved into a new circular orbit that has a radius greater than r. All right, so it's bigger, it's pushed out. As shown in the figure below, is the speed of the craft in the new orbit greater, less than, or equal to the original? So we got to go back to our formula we derived and figure it out. If the radius gets bigger, that means the numerator got bigger. If the numerator of a fraction grows, the entire fraction grows. So that means the period, oh wow, I read it wrong. It wants to know about the speed. Here's another piece of paper. We could look at this from this part of the formula. It asks about the speed. Now the radius is in the numerator. If the numerator grows, then the overall value of the fraction shrinks. That means your velocity goes down. And let's see what they say. Nope. Correct answer is less than. That's what we picked. And the explanation referred back to our derivation, which would have got us, well, you get 1 point for that.